Okay, hi everyone. Today I'll be talking about hybridization, and to make it simple for everyone and clear, I'll be using methane as my example. So with hybridization, you're always looking at the valence electron and orbitals of the atom of interest. So for this one is the carbon's valence electron. The carbon, we know there are four, two at the 2s orbitals, and two at the 2p orbitals. And then since they are at different orbitals, they also have different energy. So because of that, one would assume that the bond angles between the hydrogens would be different, but this is not the case. They are all the same, and we have a perfect tetrahedral. So this means that these orbitals actually were hybridized to be of equal energy. So to take a step back, the three hybridizations we need to know is sp, sp2, and sp3. The S stands for sigma, and the P stands for the pi bonds. And the number of orbitals, so S is 1, and then P, whatever number is on top, I can draw it like that. The number of orbitals stated in its name is equal to the number of hybridized orbitals you get at the end. So it's easy to assign a molecule to a hybridization because all you have to do is count the number of electron domains around the atom of interest. For methane, there's 1, 2, 3, and 4. So since there's 4, we know it's the sp3 hybridization. So this is when there's 4 electron domains, and likewise, this is for 3 electron domains, and this is for 2 electron domains. So now that we know that methane has an sp3 hybridization, we can go ahead and draw the four hybridized orbitals and add in our electrons. And we know that the energy level, which they're all of the same energy level, will be in between the 2s and the 2p orbitals, so somewhere in the middle there. And through this, we know that carbon has 4 unpaired electrons, which explains the carbon to hydrogen bonds. So I'm also going to show you guys some practice questions so you can practice hybridization. Okay, so these are the hybridization practice questions I've written for you all. And for all of them, the first step I've always put is draw the Lewis structure, because this will be very important and very helpful for actually figuring out the hybridization. Okay, so this is the answer for the first question. I chose water just to show that sp3 isn't limited to just tetrahedral shapes. As you can see, water is a V-bend shape. And as you can see from the hybridization, we have 2 filled orbitals, which kind of links back to the 2 lone pairs that oxygen has. So hybridization does help to understand the structures of these molecules. Okay, so this is the answer for the second question. I chose ethene as a structure, as the structure of the molecule doesn't have to have a central atom that the IB would ask for its hybridization. Though of course for this one, it doesn't really matter as they're both carbon. So since each carbon atom has 3 electron domains around it, we'll be using the sp2 hybridization, and then thus we'll get 3 hybridized orbitals at the end. However, carbon has 4 valence electrons, so there'll be 1 electron that is not hybridized in the pi orbital, and this explains the double bond between the carbons, which you know is a pi bond. Okay, so this is the answer for the third question. Drawing the Lewis structure is probably one of the most important and the first step you should do for any hybridization question, because you can actually use the Lewis structure to figure out the hybridization. As there's two electron domain, we'll be using the sp hybridization. Carbon here has two sigma bonds, so there'll be two electrons at a hybridized orbital and two double and triple bond with the nitrogen. So then there's two unhybridized electrons at the p orbital. And then at the nitrogen hybridization, we have one lone pair, and that is shown to kind of filled hybridized orbital, and of course one sigma bond with the carbon, and a double and triple bond with the carbon as well. So yeah, I can also work backwards from the structure to help you figure out the hybridization. Okay, thank you for listening.